Okay, so today's the day where we're going to start to graph cubic functions. And first of all, we'll look at these ones here. And these are cubic functions in this form or in stationary point of inflection form. Okay, so recall the quadratics have one basic form, that is, they all look parabolic. Okay, but cubic functions can vary significantly, and these ones here have what we call a point of inflection. So what they do is they come up to here like a quadratic would, and a quadratic will continue to go down here. But what these cubic functions will do, or cubic functions of this form will do, is have a stationary point here or a point of inflection here and then continue on up. Okay, they can also take on this point, this form here where we have turning point and a turning point. So in this quick exercise, we'll only consider the type of cubic with a point of inflection or a point of zero gradient. The graph of f of x equals x to the 3 has a point of inflection at the origin. So recall that's that one there. This graph can be transformed via dilations, reflections, and translations. So everything that applies to all the functions that we've done so far applies to these. So state the transformations that has undergone to become that, and hence sketch it. So what we're going to note is that that 2 means it's a translation to units, right? And this plus 4 is a translation to units up. So we know that that's the basic. So what will happen is it's going to go 2 across and it's going to go 4 units up. So let's put the stationary point there. Right, so what I anticipate is going to happen is it's going to come up through that x-intercept and continue on. Okay, so let's just get a y-intercept. So we're going to say that y equals -2 to the 3 plus 4, because I've let x be equal to 0 to get the y-intercept. Y equals -2 cubed is -8 plus 4. Y equals -4. So there's, what did I let that one be? That's 2, 4. So here's -4 down here. So what it's going to do is sweep through here and go up. Now I've got to get the x-intercept as well. So when does the x-intercept occur? Well, it's going to be when y is equal to 0. Okay, so let's take 4 from both sides. Now what I'm going to do is third root both sides. So I'm going to get the third root, that's plus the third root of -4, and I'm going to add 3 to the result. And that's solving for x. Now what is the third root of -4? I've got no idea, but what I know is that's the coordinates where that happens. So I'm going to label that as third root of -4 plus 3, 0 as my x-intercept. Right, so there's the questions for 6E, 1 and 2. That should be a little bit of revision for what we've already done. So on to the big stuff here. So these are factorized cubic functions that we're after. The general cubic function can be written in this form as cube term, squared term, x term, and constant term. And varying these coefficients A, B, C, and D will produce so many different shapes. Okay, so it's starting to get really cool. So to sketch a cubic function, if it's not in this form here, you will need to have an idea of the general shape, the y-intercept, and the x-intercepts. As with quadratics, all cubics have one y-intercept that occurs when x is equal to 0. But unlike quadratics rather, cubics always have at least one x-intercept, always, okay, and a maximum of 3 x-intercepts, okay. So here's some of the different shapes that we might get. Okay, there's 3 x-intercepts. Okay, so we're going to call this here, I'm going to call this a pos cubic. Okay, so what I mean by positive cubic is our x to the 3 term is positive. Okay, now note that when we have a positive cubic or a positive x to the 3 term, what will happen is the cubic starts with a positive gradient. So if you imagine back to linear, we've got a positive gradient. this will start with a positive gradient, i.e. as x increases, so too does y. It's very important to know that. And this is 3x ints. Okay, now let's do a neg cubic. Okay, and that would be one where the cube term is negative. All right, well, if you can anticipate that a positive cubic starts with a positive gradient, a negative cubic will start with a negative gradient. So it's going to look like that. So notice there that we've got one of those ones that gets 3x ints. All right, so here's another pos cubic. And what I'm going to do is 2x ints. Right, so it might look like this. Okay, where we've got x-intercept and x-intercept. So again, positive cubic means we've got power 3. We can have neg cubic and 2x ints as well. That's negative x to the 3. And that might look as follows. So we go down to here. Notice we start with a negative gradient there, x-intercept, x-intercept. Again, there's heaps of different variations on how this can look. So this is not all of the negative cubics with 2x-intercepts, but it's one version of what can happen. All right, and we can also get 1x-intercept as well. So this is a pos cubic, 1x-int. So remember, positive cubic starts with a positive gradient. So it can go like this, okay, where the only x-intercept is that one there. And we can draw a negative version of that. So what I'm going to do is have the turning point happen there and the other turning point there. Okay, so that's an example of a neg cubic. That's x to the 3 being negated and 1x int. Right, so these are just a wide variety of cubics that can happen. But again, the very important skill that I want you to understand is that a positive cubic always starts with a positive gradient and negative cubic always starts with a negative gradient. Right, so we're going to sketch this graph here, and in a very important disclaimer, we can only obtain the coordinates of the turning points via CAS at this stage. Later on in the year, we'll use calculus, new branch of mathematics, to find that, but at the moment, we can only use CAS to do it. The turning points of the cubic are not the midpoints of the x-intercept, so I'll go on to show you what I mean by that. Right, so here's our cubic function, so let's put it together. We've got x-intercepts at 1. So I'm just solving via the null factor law here. -1 and -2. So there's an intercept, and there's an intercept. All right, we'll grab the y-intercept as well, which is going to be -1 times 2 times 1, because I let x equal 0. And that's going to be -2 times 1 is -2. So it's going to be down there. All right, so now's the big time where we're going to sketch this thing. So what I need to know is that a positive cubic, which this would be, because if I multiply this out, in fact, I'm going to do it. I'm going to define that function. So define f of x equals x take 1, x plus 2, x plus 1. And I'm going to just expand x. And what we can see very quickly is that this x term here has a coefficient of +1. So therefore we've got a positive cubic, which always starts with a positive gradient. Okay, right, so here goes my attempt at drawing it. So what I'm going to do is start with a positive gradient, go down through the x-intercept and there. Okay, now the one thing to note here is that it does not turn on the x-intercept, so I don't like that graph. Okay, so what's going to happen with a cubic is that it never turns at the midpoint. Okay, so this one will turn either just before or just after that y-intercept there. So here's another attempt. That didn't feel right at all. That's better. Okay, so let's note the key features: -2, 0, 1, 0, -1, 0 rather, and 1, 0, and the y-intercept is 0, -2. Right, now what actually are the turning points? Well, let's go over to graph and table and graph the thing. So that's already in there, so there it is there. And what you can see here is we did pick this correctly because there's the y-intercept at -2. I might just zoom in on that a bit. We're going to do -3 to 3, say, and -3 to, I don't know, 2. All right, so we can see here that it turns just after there, okay? It doesn't turn on the midpoint. And notice here, it does kind of look like the midpoint, but I bet you it isn't. So I'm going to go analysis and gsolve, and what I want to get is, I'm going to get Fmax. No, I'm going to zoom, analysis, gsolve. I'm going to get the max, okay? So here's our maximum here at -1.549. Notice that it's not -1.5. Okay, so again, the midpoint is not the turning point. Okay, I can't stress that enough. And over here, we'll just go to the minimum. So I'm going to do analysis, gsolve, and min. Notice that the other turning point is at 0.2, not at 0. Okay, so again, that's the method that you would use with CAS. To find the turning points is you would just go into graph mode and actually pick them off the graph. All right. And we don't need to worry about labeling those turning points either. So at this stage here, it's just x-intercepts and y-intercepts. They're the only things we're really interested in. The other thing you might sort of wonder about is how high to go on that turning point. Okay, so how high should I go? I don't know. All right, go as high as the pen sort of feels right to do, if that makes sense. Okay, like if you sort of go up and you try to go really high, that's just being a bit silly and it won't allow you to sort of draw the graph properly. I'll try to show you what I mean in this next example. Okay, so sketch the graph of this. So when I solve this, what I note that's going to happen is 0 equals x squared, x take 1. The solution is going to be x equals 1 and x equals 0. But this one here is a squared solution. So that means that something special happens at this. There's going to be a bounce. Okay, that's what I call it, a bounce. Okay, so again, don't be telling your tutors that that's like a technical maths term or anything like that. A bounce is like what I think. Okay, all right, so let's see what that might look like. So at 0, we've got a bounce, and there's another x-intercept at 1. The y-intercept is obviously going to be 0 because it goes through the origin. Okay, so let's try and draw it. Now, it's a positive cubic. Positive cubics start with a positive gradient. Okay, so what it's going to do is it's going to get to this point here and bounce, turn, and cut back up. Okay, so there is that, x and y. Right, so not too difficult so far. Okay, again, notice that that turning point there is not the midpoint. All right, this thing here. All right, so we've got this here when we solve. So that's going to be x equals 1 when I solve, and x squared plus 4x plus 5 also equals 0. So what we're going to do is go ahead and try to solve that, which is, what's that, 5, 1, x. What do I need? Interesting. Okay, so I think what's happening here is it's going to have some irrational roots. Okay, so yeah, can I just confirm that? 5, that would have to be the negative, but that will make that positive. Yep, no. So yeah, this one here is going to have, okay, is it going to have a solution? Is this solvable? Okay, so I don't know. So what I'm going to do is throw the discriminant check at it. So discriminant equals b squared take 4ac, and remember that tells us whether a quadratic function has solutions, and actually it won't. Okay, discriminant is b squared, which is 16, take away 4 times 1 times 5 equals 16, take 20 equals -4. So this doesn't have any solutions, okay? So it's only got the one solution. Okay, and that happens at 1. Now, the next thing to note is this is a negative cubic. Okay, so what's going to happen is it's going to cut. Okay, there's heaps of different options here that can happen. This is a really tough sketch, this one. We've got negative. I'm going to get the y-intercept. This is going to be 0. That's going to be negative 1. When x is 0 over here, this is going to be 5. Negative, negative 5. So it's going to turn there. So this is what could happen. Okay, so what could happen is the function comes through like this and does that. Now that's one option. It could do this. Yeah, it could do that as well. Okay, so that's another option there. And to be fairly frank with you, I don't know which one it is unless I use some maths that you don't know yet, which is calculus on this. Okay, so at this stage here, we would just be guessing that it's either that or it's going to be this. All right, and the only way to find out for you guys at the moment is to jump on your calculator and get it to graph it for you. So let's find out which one it's going to be. So we wouldn't really put this one on an exam or something like that, maybe a multiple choice, which one of them could it be, and have one of these options there. Yeah, that's the only way we could really do this with the level of your knowledge at the moment. All right, so it was option 1, okay? But at this stage, if you had that or that, either is fine, okay? Even though they look like completely different graphs, you just don't have enough information at your disposal yet to be able to answer this one here, okay? And what is it, 0, 5. So only copy that one into your books, but note that if you did put that one down and I had a go at you for putting that down and, oh, don't you know where the turning point is, you would quite rightly say to me, no. Right, so another graph here, and it's in single term form. Okay, so if you thought to yourself, how do I get that into factorized form so I can get the x-intercepts? Well, it's time to use either long division or equating coefficients to attempt to factorize on this. All right, so the first thing I've got to do is find a linear factor. So I hope it doesn't take too long because I have not done this one yet. What's that? 3 take 5 is not equal to 0, so it's not p of 1. P of negative 1 is negative 1 plus 2 plus 5 takes 6, and I think this might be a goer. Negative 7 plus 7 is 0. Therefore, x plus 1 is a factor. Okay, so feel free at this point now to do some either long division or equating coefficients. I'm going to equate coefficients because I love it. X plus 1. All right, so x multiplied by what gives me x cubed? It's going to be x squared. Positive 1 multiplied by what gives me negative 6? It's going to be negative 6. And the middle term is going to be bx. How do I make an x term? I go 1 times bx, which is bx, and I go x times negative 6, which is negative 6x, equals the x term over here, negative 5x. So that's going to be b take 6 equals negative 5, b equals 1. So p of x equals x plus 1, x squared plus x take 6. Okay, again, feel really comfortable using long division on that. Again, don't sort of think that by doing that you're doing it in a really slow fashion. Had many students very successfully use long division and get a very good VCE score. So don't be thinking that you have to do equating coefficients. All right, so now what I'm going to do is try to further factorize this one here. So p of x equals x plus 1. Please tell me this goes down by the cross. X, that's the negative. X take 2, x plus 3. 0 equals x plus 1. X take 2 x plus 3. Again, very important if you're trying to show the x-intercepts or solve like this, that you do show this step. Let p of x equal 0, x is equal to -1, x is equal to 2, x is equal to -3. Many students just jump to this step from here, okay? And it's important to show this step to show that you're letting the left-hand side equal 0. Okay, so here's our intercepts. They are going to be at -3, at +2, and -1. And we've got a y-intercept here in the original form as -6, so let's just chuck it down there. All right, x term is positive, so it's going to start with a positive gradient, so it's going to start up like that. So again, I'm just going to try and do a quick attempt at it. So yeah, it doesn't feel right. We go higher and turn through the x-intercept and up there. Yeah, I'm happy with that. All right, so right, here you go. So I'm going to try and swing high through there, turn and back through there. Okay. All right, no, mine doesn't go through the x-intercept, but can you please make sure your example does? Okay, so this outlines the process of finding the x-intercepts, but I did go through that already. And these are your examples here from 6F. Okay, so get cracking on those.